Все, меня слышно?
Сейчас я скажу, проверю.
По-моему, слышно. Какой звук идет?
Раз.
Сейчас. Ладно, сейчас он проверит.
Слышно или нет? Слышно? So, okay, I continue injective objects, and today I'm going to finish this topic. So, new definition. An abelian category is called pseudo-complemented if you have the following property. For any object x in this category, so an abelian category A is pseudo-complemented if for any object x there is a subobject, and for any object and for any subobject, so for any x prime which is a subobject in x, there is a module, there is a subobject C in the X, such that we have two properties. The intersection of the C and X prime is 0. And the second property, C is maximal with respect to this property. So why this is important for what we do? Well, because we have the following lemma, which is quite easy to show. So I'm going to leave this as an exercise. So an AB5 category is pseudo-complemented. So this is just one of the properties of AB5 categories. So mostly we're going to study today injective objects in AB5 categories, more specifically in Grothendieck categories. And this property being pseudo-complemented is quite useful, well, if you try to say formulate what are the minimal requirements and what you're going to use in the proofs. So you can as well just forget about this AB5 and formulate everything for pseudo-complemented. Okay. So here's the first proposition. So let A be pseudo-complemented. So then, in this case, an object I is injective if and only if any essential extension of I is an isomorphism. So that's a very useful characterization of injective objects. Okay, so in one direction, if I know that I is injective, the proof is very simple. So I take I, suppose I have some essential extension, let's call this X. Well, then, since I is injective, X is necessarily a direct sum of I plus some complement X prime. But the intersection of this complement X prime with the I is 0. Hence, X prime is 0. So everything immediately follows because this arrow from I to X is essential extension. Okay, in the other direction, it's a little bit more interesting. So I want to show that the object is injective if we have this property. Well, let's take object I. So embed this into some x, and x modulo I is the quotient. So one of the characterizations of injective objects was that any short exact sequence with I in the beginning splits. So I want to show that any such sequence splits. That would be enough to finish the proof. So here, so I is a sub-object in the X. So I can choose a complement. So C is a complement to the I. And there is a also map to the quotient by the complement. So let's call this map F, and the map to the quotient call pi. So here we can form a pullback, but the pullback gives us the intersection, and we know that for the complement the intersection is 0. So we have 0. Now we apply lemma 2 from the diagram lemmas. So lemma 2 in this case. So remember that was okay. If you just rotate this and maybe reflect this, that would be the same diagram. So it states that if you have a pullback here, then the kernel of this composition is exactly this object here. So we can say that the lemma 2 implies that the kernel of the composition of pi and f is 0. Okay. Now, well, if I want to understand a sub-object, so what I want to show now, I want to show that I see that this composition, f and pi, this is a monomorphism since the kernel is 0. So I want to show that this actually is essential extension. So the goal is to show that this is essential extension. So for this I need to take a sub-object here, right? But any sub-object here looks like y modulo c. This is the fourth isomorphism theorem. But if y is not equal to x, then y intersection with I is not 0. Well, this is by maximality of this complement C. Okay. But that's exactly what we need, right? We take a sub-object. Well, pre-image here will be just y, and then take intersection with I, and this intersection is not equal to 0. Hence, the composition pi and f is essential extension. Now, we know by assumption of this proposition that any essential extension is an isomorphism, right? So this is an isomorphism, so there is a map in the other direction. So I can construct the retraction, which will be pi f inverse composition with pi. So clearly, if I take composition of this R with F, I'll get the identity. So hence this is the retraction, and this thing splits. Okay, next proposition. If abelian category A has enough injectives and pseudo-complemented, then A Yeah, I think everything fine. Yeah, so if A has enough injectives and it's also pseudo-complemented, then A has injective hulls. Okay, so take an object X. I want to construct an injective hull of this object. Well, first of all, I know that this can be embedded into some injective object. This is because I have enough injectives. Now, let's take a complement. So C is a complement of X in I. So the intersection of the C and X is 0 and C is maximal with respect to this property. Well, the next step is to take I bar, so is a complement of the C of the C in I such that X is contained in the I bar. So C intersect this I bar is 0, I bar is maximal with respect to this property, and also I bar contains X. So the additional requirement that X is contained in the I bar is not a problem, because you can always go to the quotient by the X and apply, say, fourth isomorphism theorem. Well, or you can then go back to this lemma, come up with a proof, and you see that you can modify this proof to include this additional requirement. It also could work. Okay, so now I have the following. Well, first of all, I claim that this I bar that contains X is precisely the injective hull. So what we want to show that I bar is an injective hull of the object X. So this is our goal. Well, first observation is the following. Well, I need to check that this is essential extension, right? So the first step would be X containing in the I bar is the essential extension. Well, let's take an object, X prime, which is not a zero object, and this is a sub-object in the I bar. Well, what I can say? Well, first of all, if I take the intersection of the X, and C plus X prime, then this is not zero. Well, and this is because C is maximal with respect to this property. So this object is a little bit larger than C, so the intersection has to be non-zero. Of course, notice that it's important here that X prime is not contained in the C, but it is of course true since actually X prime is contained in the I bar, and intersection of the I bar with C is 0. Okay, so this intersection is non-zero. I can rewrite this intersection by adding I bar. So X intersect I bar intersect C plus X prime. Well, this is the same thing since the X is just a sub-object in the I bar, so it doesn't change anything. But now for this second intersection, I want to apply the modular law that we discussed 2 weeks ago on the seminar. And this gives us the following. So I still have X intersection. Now applying the modular law, give me X prime plus I bar intersect this C. Well, C intersect this I bar is 0. So this is X intersect with X bar. And that is not 0. So we finished the proof of the first claim that this is the essential extension. Now, the second step would be to show that I bar is injective. Okay. Well, to do this, I'm going to use previous proposition. So in the pseudo-complemented case, I know that I can characterize injective objects by that there are no essential extensions of them. So let's take any essential extension. So let's call this T. So T is any essential extension of the I bar. If I can show that T coincide with the I bar, I'm done with the proof. Well, I bar is a sub-object by construction of the injective module I. Hence, I can extend this to the T, and this still will be an embedding. That was one of the statements that I proved at the end of the last lecture. That for essential extensions, you can extend these maps, but if you start with the monomorphism, you still get the monomorphism. Okay. Well, the claim is that if you take the intersection of the T and C, this is 0. Well, that is because if you say that intersection of T and C is not 0, well, this implies immediately that the intersection of the T and C and I bar is not 0. Right? Since I assume that this essential extension, the intersection of T and C is sub-object here. So hence the intersection is I bar is not 0. Right? So here I use that. Well, let's maybe call this temporarily map psi. So psi is essential extension. So now the reason here for this implication is that psi is essential extension. Okay, and that's a contradiction, right? Because we know that the intersection of the C and I bar is 0. So this can't happen. So the intersection of the T and C is 0. Well, but then by maximality of the I bar, T has to coincide with I bar. T is a maximum module that has this property. And that's the end of the proof. So I bar is injective by previous proposition. Okay. So now I'm going to prove one fundamental theorem about the existence of injective, enough injectives and injective envelopes. So a growth-empty category A with generator G. So recall that the growth-empty category is an AB5 category with a generator. So here I'm not saying that I additionally have a generator. Essentially, I'm just giving a name to this generator in the statement. So has enough injectives. Okay, proof. Now, essentially, proof consists of two parts. So in the first part, I'm doing the following. I'm using axiom of choice, so by the AC, for any x which is an object in this category, I can choose the essential extension. So choose essential extension, E of x. Well, of course, we know that if x is injective, then there are no such essential extensions. So then we just take E of x to be equal to x. But if x is not injective, we choose proper essential extension. Well, if object, this is exactly what I have here as a comment. If the object is injective, if and only if there are no essential extensions. So for injectives, well, I just don't do anything. And if it's not injective, there is a proper extension, so I choose one of the proper extensions. Okay, now I'm going to do the following induction. So let me call epsilon 0 to be the map that I obtained just on the previous step. And then I want to continue constructing such maps for all ordinals. So if I have epsilon omega plus 1, then I define this map as follows. This will be just the composition. X has an essential monomorphism to the E omega, and then there is an essential monomorphism of the E sub omega. So this is what you do for the successor ordinals. Now for the limiting ordinals, you just use the following definition. E sub omega is the direct limit over all ordinals eta less than omega of the E sub eta. So of course this would be just the same as the sum of the E sub eta, eta less than omega. So with these two definitions, we kind of defined this chain of the essential extensions for all ordinals. Okay, now let's take a T, which is a non-zero object, in the E sub omega. Well, well, first of all, it's clear that, well, of course, E0 is essential extension by definition. This is essential extension because we know that the composition of two essential extensions is essential extension. So what I want to show that actually a map from the X to the E omega is again an essential extension. So for this, I take a non-zero object, subobject in the E omega. So then, well, T is the same as T intersect with the sum E sub eta, eta less than omega. Now I use AB5 condition in one of the forms. This is the sum of the T intersect with the E sub eta, so eta less than omega. Well, then I can. No, this is just some ordinal, a limiting ordinal. Yeah, so I want to show that the extension in the case of the limiting ordinal is essential. So I choose an object, I'm going to consider intersections. So, but first I can notice that T is non-zero, hence there is summand here which is not equal to 0. So there is eta such that T prime, which is T intersect with the E eta, is not equal to 0. Well, then we have immediately several observations. Well, we have X mapped to the E eta and E mu maps to the E eta. Well, these are essential extensions. Well, since these are essential extensions, we can claim that the T prime intersect with the E mu is not equal to 0, and also T prime intersect this X is not equal to 0. Well, but if this is true for some sub-object T prime of the object T, I can immediately conclude that the T intersection with the E mu is not 0, T intersection with X is not 0. Well, and this means that the map X, which is embedding into the E omega, is the essential extension. So this is kind of the first part of the argument, working with these chains of extensions. Well, by construction, I know that these are essential extensions because I obtained this on the previous steps. Now, I have an object T prime, which is sub-object here or here. So then I can, by the fact that it's essential extensions, I can say these two intersections are non-zero. By definition of essential extension, I take a non-zero sub-object here, take intersection with X. This is non-zero. So T prime is a sub-object in T, so if I replace this with T, this is still true. Hence, I can conclude that this thing is the essential extension. Okay, so the second step is the following. I introduce the ring, so R is the endomorphism ring in the category A of the generator G. So then there is a functor H sub G from the category A to the right modules over R. So, do you see why this is actually right modules? Well, if you take some, say, X, which is an object in A, right, then this functor H sub G of X, these are just all maps from the G to the X. But you can take this element, well, first of all, by definition, this is an abelian group, but if I take an element, say, little m in this abelian group, then if I have another element, little r, from this ring R, then I can take the composition, and this will be, again, an element in this H sub G of X. So this defines an action of the ring of this on this module. And also notice that it's actually the right action, because if I write R2 here, G and R1, so then since the composition is associative in the category, I have the following, M R2 R1, M R2 R1. So I have this by the definition, by the definition of category, essentially, right? In the categories, I have associativity property, but that's exactly the same associativity property that you have for the right modules. So hence, indeed, these are right modules, not left modules. So let's take an essential extension. So X prime in the X. This is the essential extension. So this is in the category A. So then I want to show that this implies that the H sub G of the X prime, H sub G X, this is again essential extension, but now in the category of R modules, right R modules. So this is what I want to show again. This is want to show. Okay, so let's complete this essential extension to the short exact sequence. So then we know that the H sub G is the left exact functor. So let me also call this essential extension F. I'm going to need this notation later. So then, if I have this, I have 0 H sub G of the X prime, H sub G of X, H sub G of the quotient. So the left exactness of this functor, of the home functor. So let's take N to be a submodule here. So right, I want to show that the intersection of this N with the submodule H sub G of the X prime is not 0. So let's take also an element phi here, which is not 0. Of course, N is not 0, otherwise I can check the condition. Okay, so then I have the following. I have X prime, which is mapped to the X with the map F, and I also have map phi, which is a map from the G to the X. So let's take pullback. The pullback is just by definition of the inverse, so this is phi inverse of the x prime. I'm going to call the corresponding maps f prime and phi prime. Okay? Well, I claim that phi inverse of the x prime is not equal to 0. Well, this follows because f is the essential extension, and now you just look at the sub-object here, which is the, let's say, image of phi. Yeah, so this is since f essential extension, x prime intersect with the image of phi is not equal to 0. Hence, this thing is not equal to 0 because that would contradict this last condition. Okay, so that's a non-zero object. Now I know that G is the generator, so this composition, phi prime and phi, this is non-zero map. Hence, from the generator G, there is a map H such that this composition is not zero. So let me write this. Phi f prime H is not equal to 0. But essentially we finished the proof because this thing is an element in the N intersect the image of the f with a lower star. So f with a lower star is just the map here.
Можете чуть-чуть назвать, что вообще такое фи?
Well, I choose a non-zero submodule here, right? It has a non-zero element phi here. But by definition, what we have here, these are maps from the G to X. So phi is a map from G to X. That's what I'm using in the construction. Right, so this composition of the f prime and phi is not zero map. Hence, there is a map from the generator. Let's call this as usually H. So then this whole composition is not zero. Now the only thing we need to understand is why this composition of three maps is actually in the N and also in the image of the phi lower star. Well, why this is in the N? Is it clear why this is in the N? Well, phi was in the N, and then we take just product with the phi prime H and the f prime H, and this is this map, right? So this map, but this is exactly an element in the ring. Hence, because R is a right submodule, this is in the N. Okay. And why this is in the image of the f lower star? Well, this is because this square is commutative. So I have this map. I can as well think about this as this map, but this is precisely a map from the G to the x prime composition with the f, which is exactly the application of the f lower star. So this intersection is not zero. Well, because N is not just subset, is the submodule, which is right submodule. So here I have phi, an element in the right submodule, product from with the element of the ring. Right. So this composition, this is a map from G to G, which is an element in the ring by definition of the ring R. Well, yeah. So we finished the proof of this claim, but it's not the end of the proof of the theorem. Okay, maybe let me rewrite this to save some space. So this is an element in the N intersect with the image f lower star. No, this is just a map that is induced by this map, right? So here we have a map from G to the x prime, take composition with F, that is F low star. Well, that is because you take this composition of three maps and you think about this as a composition of these three maps. So that's exactly a map from the G to the X prime composed with F. So this is F low star applied to this map. Okay, so we prove this claim that this functor H sub G maps essential extensions to essential extensions. Well, the rest of the proof is more or less straightforward, right? The idea is, well, the idea is the following. Take H sub G of the X. This is some right module. This can be embedded into an injective module. So now I assume that we already know that the statement is true for modules. So that's something actually we need to do in the seminar separately without using this theorem. So, but we can use this in the proof. So, in fact, I actually gave you a statement what's the injective code generator from this statement. It's easy to derive that there are enough injectives. So what we actually need to show that we have an injective code generator in the modules. Okay, but anyway, so we can take this thing and embed it into some injective module. But then we can apply transfinite induction and say that for any ordinal, this is also embedded into the same injective module. Okay. Oh, this is using that for any ordinal we have essential extension. This functor preserves essential extensions, and we also use that proposition from the end of the last lecture that if you have essential extension embedding into injective, you can extend this and still get an embedding. But that's a contradiction, right? Well, if you have this infinite chain that works for any ordinal, this is just contradicts the, well, contradicts this embedding by cardinality reasons. It's not possible to embed this for any ordinal to this fixed module I that has some fixed cardinality. Hence, those chains of extensions that we constructed in the first part of the proof actually stabilizing. So there is something like maximal E omega of the X. But since this is maximal, there are no essential extensions of this object. By what we proved before, it means that this is actually an injective object in the category. So, previous proposition. Okay, there's previous proposition or the one before. Oh, not the previous, but the one before, right? Okay, right. This thing is injective in the category A. The end of the proof. Oh, well, just to be precise, I'm going to formulate two corollaries which doesn't require any proof. You'll get this for free. Or just important to notice that we have this. So, corollary. If A is the growth in the category, then we have two things. So first, A has injective house, and two, A has injective code generator. There are observations that we get for free because we actually proved these two things before. Well, the fact that it has injective house, that's exactly previous proposition. We have enough injectives, This is what AB5, hence pseudo complement, and hence everything works. So, and the fact that we have injective code generator, we proved on the 2 weeks ago. There was a statement that if you have something like AB3 condition and enough injectives, then you have injective code generator. So this is essentially just a summary of what we already know. Okay, and that's all I want to say about the general theory of injective modules, or injective objects. Injective modules we're going to do with more details on the seminar. So next section. Finiteness conditions. So in this section, if I'm talking about category A, then A is the Grothendieck category. So definition. Well, essentially what I'm going to do in this section, you know that for modules, there are kind of two important finiteness conditions. Well, first, the module is finitely generated, and the second is module finitely presented. So in the general, say, Grothendieck category, it's not clear what would be the analog, right? Because we don't have elements. It's not possible to say it's generated by finitely many elements. Well, there are actually two general conditions that can be formulated in any Grothendieck category, which are equivalent, and in the case when n is a category of modules, actually give you the standard definition of the well, actually they are equivalent to the standard definition of finitely generated module. So an object X in some Grothendieck category is called finitely generated. I'm going to write just Fg for shortness. If we have the following, whenever I can write this X as a sum of sub-objects, and these sub-objects is a directed set, then there is an index I0 such that, say, this is our directed set I, then I0 in the I, such that X is X I0. Or as you can see, even if A is the category of modules or something, well, it's some exercise to show this equivalent to the standard definition. It's not something completely trivial. Again, something that we're going to do in the seminar. Okay, so first proposition about finitely generated modules. So suppose we have a short exact sequence. So then, two observations. If X is finitely generated, then X double prime is finitely generated. So you know this for modules, the quotient of finitely generated module is finitely generated. And the second statement is that if X prime and X double prime are finitely generated, then X is finitely generated. So sometimes people formulate the shorter and that finitely generated objects closed under taking extensions. And so this X is called an extension of the X double prime by the object X prime. Okay, let's prove this. Proof of the first part. Okay, so let's take X double prime. Say that this is the sum of sub-objects Xi double prime. Well, now I want to define object Xi. So that is by definition. So let me give a name for this map. map from x to the x double prime, I'm going to call f. So then xi is the f inverse of the xi double prime. So this is some sub-object in the x. So then, using fourth isomorphism theorem, I can say that x double prime I is isomorphic to the xi modulo x prime. Okay, so then this set xi that I constructed is directed. Now that's a trivial observation because f inverse preserves the inclusions. So this is directed. And what I can say, the sum of the xi's, well, let's keep the sum, plug in the definition. Now use the fact that this is AB5 category. So this will be the same thing as the f inverse of the sum. Okay. So, and this last sum is just the same thing as x double prime. And this f inverse of the x double prime is just x. Okay. So what we see, we actually started with some presentation as a sum for the x double prime, and we constructed such presentation for the x. And we know that x is finally generated. Hence, there is I naught in the I such that x is the x sub I naught. So, and finally, x double prime is the quotient of the x I naught modulo x prime. X double prime is the quotient of the x modulo x prime, so we have this. And by the definition, well, not by the definition, but with the property that we have here by the fourth isomorphism theorem, this is the same thing, which is x double prime of the I naught. That's exactly what we want. Okay, so the second statement. Two. So I want to show that x is finitely generated. So let's say x is the sum of some xi's. Now x prime is isomorphic to the x prime intersect with the sum of the xi's. Oh, let's see. Right, so this is tautological observation. But again, using that we have AB5 category, this is the sum of the x prime intersect xi. Okay. So we presented x prime as the sum. Hence, there is, now I'm going to need two indices, so let's call the first index I1. So there is I1 in the I such that x prime is equal to the x prime intersect x I1. Well, if we have this, equivalently, we can say that the x prime is a sub-object in the x I1. Okay, this is for the x prime. Now let's go to the x double prime. Well, this is the f of the sum of the xi's. Oh, x double prime is the image of the map f, and this is just another way to write the image. Now I can rewrite this a little bit. I can take the sum over I greater or equal than I1. Okay, this is still the same sum because this is a directed set. But now I want to commute the sum and f, and this I can do in any category. So this will be the sum. Oh, any category, so which is co-complete. Okay. So f of the xi. Well, this thing I can rewrite again using the fourth isomorphism theorem as the xi modulo x prime. So again, I presented x double prime as some sum. So there is another index I2 such that x double prime is isomorphic to the, well, actually I can even say that I2 is greater or equal than I1. So the x double prime is isomorphic to the x I2 modulo x prime. Okay. So there is one more step just to organize this data that we obtained in the form of the diagram and then use 3x3 lemma. So here we have 0, x prime, x double prime 0. So inside we have xi2, this is sub-object, and there is some potential quotient. But now here I have x prime, so this map is just an isomorphism. There is a map here, and there is an xi2 quotient by the x prime, and there is a map here, which is again in isomorphism. So this kind of very trivial case of a 3x3 lemma. We have 0 here and here. So everything is exact, hence this last thing with two arrows, or sorry, with two zeros here, is also has to be exact. But this is exact if and only if this term is 0. So 3x3 lemma implies that x is isomorphic to the x I2. And that's precisely what we want. Okay. Next proposition. So x is finitely generated if and only if the canonical map from the direct limit of the a x yi. So let's call this canonical map T sub x to the a x, the sum yi, is an isomorphism for any directed set of sub-objects of some object y. So another way to characterize finitely generated objects in terms of preserving some very special colimits. In this case, colimits being just the sums of some objects of that over directed sets. Okay, maybe I start with the following. I'll just give a definition of how we get this map T sub x. Well, we have canonical coprojections to the directed limit and we also have canonical monomorphisms J sub I of the y sub I to the sum of all yi's. Right? Now, Tx is a map from the colimit. Remember that directed limits are colimits. So if I want to define such a map, I need to say what are compositions with the canonical coprojections. So here I'm going to say that the composition T sub x and the ui, this is H sub x of the Ji. Well, you can think about this in a very straightforward way. So here you have a, say, you forget about the limit, you just take an individual term, you have a map from x to the yi, right? So then we have this map, and then just take composition, and this gives you a map here. And then if you know this map on each of the objects here, well, this is colimit, there is a map on the colimit. Well, first claim is that T sub x is always monomorphism without any assumptions on the object x. Well, I think this is straightforward because what you do, well, you just take a map, you take a composition with a monomorphism. This is a monomorphism because if the composition is 0, this is monomorphism, hence the map is 0. So this is always monomorphism. So this claim about isomorphism is actually just a claim about the epimorphism. Okay, so let's do the proof in one direction. So here I assume that x is finitely generated. So let's take a map x to the sum of the yi's. So let's call this map again f. Well then, x is the image of the sum so then this is isomorphic to the sum of the two images. So now we use that x is finitely generated to say that there is index I naught in the I such that x is isomorphic to the f inverse of the y I naught. Okay, does it make sense? Okay, but if we have this, it actually means that the map we started with, this map f, is actually a composition of two maps. So there is a map from the x to the y I naught. So let's call this f prime. And then this, of course, has a canonical map, canonical monomorphism j sub I naught to the sum. So this composition, well, you see that this map factors through the yi naught. So this composition is F. But if we have this, this means that the T sub x is an epimorphism. I started with any map from the right-hand side, and I presented this as an image of the T sub x, which is I take a particular map, I take composition with this canonical map, and I get my given map. So T sub x is epimorphism. And this finishes the proof in one direction. Well, I take any map here, I call this F, and I see that this is actually F prime that lives here for some particular index to which I apply T sub x. Applying T sub x is just taking the composition with this canonical map.
То есть это просто селекция, как
Yeah, so here the value of this functor is just an abelian group. So if we talk about abelian groups on the left-hand side, on the right-hand side, you can equivalently say this is surjective map for abelian groups, yes. So let's go in that direction. So here I suppose that x is the sum of sub-objects xi. I want to show that there is a particular index I0. Well, since I have this isomorphism, directed limit of the A, now for the object y, I'm going to take again x, and for the sub-objects, I'm going to take the sub-objects xi. So hence, I'll get this isomorphism. Right? And on the right-hand side, I have a distinguished element, which is just the identity on the x. So now I see that the identity on the x is kind of live in this left-hand side, which is the directed limit. So this is what I'm going to use. Okay. Well, here's the claim. So there is map G from the x to the xi such that the composition, xi not, such that the composition is precisely this identity map. Well, now this requires some little argument to show that there is this map G. Well, first of all, as I mentioned before, here we just talk about the abelian groups. So, and we know that any colimit is actually a quotient of the direct sum of abelian groups. So we have this. This by the general observations that, you know, remember there was a general statement that any limit we can present as the equalizer for two maps. For colimits, this is equalizer for two maps, but this is abelian situation, or even in additive situation, any co-equalizer just reduced to the co-kernel. So there is some kind of sub-abelian group here, such that the quotient by the sub-abelian group gives us the limit. Well, since this is an isomorphism, the identity, well, I can think about this as some element. Well, to be completely precise, I think I need to write what T sub x inverse, but well, morally, this is the identity under this isomorphism, right? So then this can be lifted to an element here. But remember, this is a direct sum of abelian groups, so this lift, this potential lift, actually have only finitely many, let's say this potential lift Gi, right? There's some vector here, and this has only finitely many non-zero components. But now we use that this is a directed set. So if I have x, which is, I have maps to the xi1, xin, right? Well, by definition of the directed set for any pair of arrows, I can find another object, right? So I have another object, say xi naught, such that we have this commutative diagram. But if I know this for 2, I know this definitely for finitely many, and I only have finitely many. So instead of working with this whole family, I can just work with this one map, and this one map is just exactly what I call map G. Okay, so there is this map G such that the composition, or in other words, taking this composition, is precisely the applying T sub x, give me the identity. So this is kind of the lift of this identity here, using that this thing is directed and finitely many components in the coproduct of abelian groups. I can reduce everything to just one map G. Okay, but we're almost done. We have x, then map G, x I naught, then G I naught, sum of the xi. Well, if we just look at this identity, I claim that it's immediately clear that G is a monomorphism. So this implies that G is mono. So G is mono, this map is monomorphism. So what we have, and the composition is the identity. Hence, actually, I claim that these two maps are isomorphisms. So, hence, J I naught is an isomorphism. So if you want a more general version, what I'm using to conclude that this map is an isomorphism, this is the following. So let me formulate this as a remark. I have sub-object with some map G inside Y, and this is again X, and this map F. So two monomorphisms. The composition F and G is equal to 1. So then I take the composition with F, I'll get F, G, F is equal to F, and use that F is monomorphism. So G, F is 1. So this very simple argument shows that if you have a situation that you have two monomorphisms and the composition is the identity, and this is the identity, so this thing X and the sum of xi, this is the same object. Well, actually, it's not completely true, right? Since I have this isomorphism between X and this sum, so it's not the identity, it's just this isomorphism. But, well, I can kind of, if I replace this 1 by the isomorphism, I guess nothing really changes in the argument. I can always take this isomorphism and say, move it to the F and change the definition of F. So anyway, this is the proof of this proposition. And I want to finish with the definition and one elementary observation. A Grothendieck category A is called locally finitely generated. If it has a set of finitely generated generators. Now, immediately we have a proposition that we can characterize this property in other terms. So A is locally finitely generated if and only if for any object in this category we have the following. X can be written as a sum of the xi's where xi is, so the set of all these xi's is the directed set of all finitely generated subobjects. Of X. Okay, proof. It's actually not very hard. Well, in one direction, so suppose this is locally finitely generated and I want to take any object and prove this property. Well, one of the property of a generator was the following. I can take some sufficiently well, how it was G to the some set S, right? This is for sufficiently large set S. I take as many coproducts and I'll get the epimorphism to any object X. That we characterize this in the general category theory. Well, here I don't have an object, I have a set of generating objects. So I want to modify this formula just a little bit. So instead of 1x, I'll get this whole family, G sub k. I'll take coproducts over k. And then for each k, well, potentially, it could be several copies of this element gk. Just a variation on for the previous formula. Okay. Well, I claim that let's call this map Q. So that the image of Q is actually contained in the sum of the xi's. Right? Well, because if you just look at the image of this map, you'll get something like the sum. So image of Q, this will be the sum over K, and well, of the Q G of K. Well, potentially you need to take the second sum over I sub K. Right? This is by the definition of the sum. But each Q of the G sub K is a finitely generated module, because that was a proposition about finitely generated modules. Quotient of finitely generated is finitely generated, and image is the quotient by the kernel. Hence, we have this. Right? But on the other hand, this Q is an epimorphism. So Q is epi implies that the X is the sum of xi's. So this finishes the proof in one direction, and in the other direction it's even easier. So here I have this property for every object, and I want to construct this family of finitely generated.
Назад чуть-чуть, извините, что такое ИКТ?
Well, it's just some powers that I have in this formula. Right? A priori, I don't know that it would be enough to take just one copy. So potentially there are some repetitions. Well, this formula has nothing to do with this finitely generated. It's only saying that this is a generating set.
Почему для этого нужна степень все-таки?
Well, it's just a refinement of the formula. I can say that if I take this coproduct, it exists, right? And this will be a generator. So this would mean that I can find sufficiently high power such that I'll get an epimorphism to the X. Well, that was one of the, I think the only one condition that we discussed, that equivalent being for being, if you have a G generator, one of the ways to say this is to say that for any X there is set S such that G to the S has an epimorphism to the X. So now you have a family of generators. I take the coproduct, this will be a generator. So for this generator there is this sufficiently high power by this property. Yeah, I'm just saying that it's not necessarily true that all this, we need to take all these powers here the same, being equal to S. So potentially for each K we can just choose small sets that works. Yeah, so in the other direction, we have this for any object. So let's apply this in particular to the object, which is a generator, right? So the assumption here is that A is the Grothendieck category, so it has a generator. So G is the generator of A. So we can present this as the sum of sub-objects Gi. And this is the family. So this is a set of finitely generated generators. All of them finitely generated by the construction, right? So these objects are finitely generated. And if G generates everything, then the sum of this thing generates everything. Okay? Well, I think it's time for a break. Well, we proved in general that if you have a family of injective objects, then if you take the product, the product is again injective. That was quite kind of general property. Now there is an interesting question. So for modules, so let R be a left Noetherian ring. So IK is a family, so is a set of injective R modules. Well, let's say left R modules, injective left. Then in this case, you can take the coproduct. So on modules, this is usually a direct sum. And this is again injective. So in fact, this is if and only if condition. Ring is left Noetherian if and only if we have this property. In one direction we can do on the seminar, in the other direction it's much harder, so it's in the first assignment with the hard problems. We assume that the ring is left Noetherian. We want to show that direct sum of injectives is injective. No, I think it goes without saying that the first thing you need to try when you deal with injective modules is to formulate and try to apply the Bayer's criterion. По-русски Bayera.
Что?
Well, it's a statement that if you have a ring and then they have an ideal in this ring, and you know that for any map to the injective module from the ideal, you can extend to the ring, then this works for any. Well, if you have this extension property for an object, then this is actually an injective object. Maybe I need to write this. So J is an ideal in the ring. You have a map to the I, and then you know that you have an extension. Then this I is injective. We prove this in a more general situation when you have a abelian category with a generator and this property, but in the case of modules over ring, this is what it's saying. Yeah, so it's enough to take an ideal J. You have this map to the direct sum. You somehow want to extend this, but you know that the ring is left Noetherian. One of the ways to say this is to say that any left ideal is finally generated.
Если мы научимся расширять вообще, чуть больше говорить, то безотносительность это сразу все.
No, it's not how I would do this. No, you can extend from any ideal to the ring using that this ideal is finally generated.
Зачем тогда вообще не озвучивать?
To say that the ideal is finally generated.
Да.
So you have a solution? Okay.
So if we take all components in all these parts for all these elements, we'll have only finitely many IKs, so we have something like and there is the product is the same thing as coproduct is the same thing as sum. So we have such thing and we have such inclusion.
Mhm.
So we have extension in this way.
Yeah. Questions? Okay, so now let's R be a domain. So there are no zero divisors. So recall that M module over R is divisible if we have the following. We take any M, or little m in the M, which is not a zero element, and then we can write this M as an R M prime for any R in the ring, again non-zero. Well, I guess for the little m, I can as well just take a zero. Well, it will be a trivial observation that zero is a product of any element, and again zero. So essentially, I can take any element in the module and divide this by R. That's what it's saying. So the problem is to show that if R is a domain, then if I is injective module, then I is divisible. Да. Okay, maybe we need to give more time. Maybe I can formulate another problem. Not about modules, but about functors. Well, sometimes people consider modules or additive categories, in particular over abelian categories, and that would be just by definition all additive functors from the given category to the category of abelian groups. So, and it's actually more or less straightforward to check that this category of modules is again abelian if A is abelian, and moreover, if A is satisfying ABN conditions, then this category is also satisfying ABN conditions. But what I want you to check is that if you take injective objects in the category of modules over a category, that any injective object is actually a right exact functor.
Я вторую сама не знаю,
Почему нет?
G главный четвертый элемент.
Можно посмотреть, well, you can take this domain, right, and then you'll get this short exact sequence with just multiplication on R. Since this is not a zero divisor, there is no kernel, as this is indeed an exact sequence. Now you take some injective module, right, and you want to show that this is divisible. So take a map here from a ring to injective module. Well, since this is just a free module on one generator, this map is completely determined by where one of the ring is going, right? So now you know that for injective, you have this extension. Just look at this diagram and you can see that this is divisible. А, вот это? Это те самые, все аддитивные функторы.
Все единые.
Так, а с этой вы разобрались, вот с этой с диаграммой? Расскажите тогда.
Так вы же уже все сказали.
Ну, не до конца же.
Ну, ладно, нет, до конца я, конечно, тоже не расскажу. То есть,
Ну, там еще какое-то вычисление все-таки надо сделать. Хоть оно в одну строчку, но тем не менее.
почти звучит.
Нет, то, что я сказал, это как бы еще не полное решение. Так, это правильная коммутативная диаграмма, которую можно рассмотреть.
Ну да, потому что единицы. Что такое? Ну, это что-то порождается тем, куда переходит единица. У нас же с единицы конца, правда?
Да, да.
Супер. Значит, единицу переводим в n. Ну, если сейчас. То есть отрицание. Ну, наверное, от противного, да.
Сейчас, зачем от противного?
Ну, что. Не важно. Хорошо. Да. То есть у нас есть вот n, за которым мы это ищем, когда мы его переводим в единицу.
Угу.
У нас получилось здесь предложение. В силу индуктивности есть вот это продолжение. Соответственно, вот здесь тоже есть прообраз m. Ну просто потому что иначе вот это какое-то проявление дает. Это f от r. Да, f от r должно быть равно.
Угу. Ну, просто коммутативность, да.
Ну да. Дальше это значит, что... Сейчас. Запуталась. Ну и опять сила коммутативности. Тогда... Ой, нет. Извините, я запуталась.
Ну, здесь негде запутаться, у вас 3 буквы в формуле. Ну, вы знаете, что f это же отображение модулей, да? Оно линейное.
Да, f линейно же точно. Вот тогда f... Это вот... единица. Ну да, это единица просто, да. Ну вот это вот.
Да? f от единицы это есть искомый m'. Да.
Единица.
Well, in the other direction, suppose that R is a principal ideal domain and M is an R module. Well, left or right, we can assume that the ring is commutative, the argument is still the same. So M is an R module, then M is divisible implies that M is injective. So our principal ideal domains, being divisible, being injective, is the same thing. Вы решили? Расскажите.
Ну, достаточно доказать, что любого идеала F и отображения вот такого, его можно продолжить.
Угу.
Но его можно продолжить, потому что это главный идеал, и он divisible. То есть, вот, G зашелся предельно G маленьким, когда здесь, ну, это отображение взаимно однозначно, такие отображения взаимно однозначно соответствие, куда приходит G маленькая. Вот. Ну, мы знаем, что, например, в ПТМ мы знаем, что существует там штрих такой, что G штрих равно n. Мы, соответственно, берем здесь единицу и вводим ее в штрих. Победа.
Угу. Okay. So finally, we can solve this question that I proposed maybe a month ago, that the Q modulo Z is an injective cogenerator in the category of abelian groups. It's important even from the theoretical point of view.
Который инжектор motion.
Да. No, I think the fact that this is injective is more or less clear because, well, we know this is the same as being divisible, so this is clearly divisible. So we only need to show this actually a cogenerator. Ну, расскажите, посмотрим.
Ну, если я правильно понимаю, что это такой генератор, нам нужно до любых, если у нас есть f уже, то есть h в кусок такое, что hf не равно h, правда?
Это правда, но я хочу это прокомментировать. Well, first of all, this is additive case, so you can, you can assume that g is 0, so equivalent condition would be for any non-zero map here, you have a map such that the composition is non-zero. Yeah, I mean, even more we can say, in general, suppose we have a category where we have a notion of a zero map. So then we can say that the Q is a cogenerator if and only if we have the following property. They say if this is category C, X, so all the maps from the X to the Q are non-zero if X is non-zero. This is an equivalent way to formulate the same thing. Well, why this is true? Well, that is because you have X, and then you have the identity map on X. So if X is non-zero, there is not a zero map. Hence, there is a map from X to the Q, well, right, H, such that this composition is not zero. So this composition is just the same map. So this map is not zero. So this is an equivalent way to say what's a cogenerator if you can talk about zero maps and zero objects. So for example, in any additive category.
А следствие отсюда сюда как устроено?
Do we need to prove something?
Ну просто у меня впечатление, что это какое-то очень более слабое условие, нет?
No, I think this is exactly equivalent condition. What you want to show that, well, if this is a cogenerator, then we have this, right? If we have this, then this is a cogenerator. Well, you want to say that we now want to take any map, any non-zero map, right? And we want to show that there is a map to the cogenerator.
Не, стоп. Если у нас нет разности, или мы считаем, что у нас есть разность. Если у нас нет разности, то я вообще не вижу, почему мы можем говорить про одно отображение здесь. Типа, если у нас есть 0, но непонятно, что такое f минус g, то все-таки придется, наверное, говорить про f и g. Нет?
Okay. A is additive.
Okay.
In this remark, so that there is a difference between maps. But yeah, I think you're right. We still need to show something. We need to say that if we have x and y and a map between x and y, if I want to show that this is a cogenerator, right? What I need to show? I need to show that this composition, so f is not zero, then this composition is not zero, right? Well, and I only know this property.
Нет, наоборот, мы знаем вот это, мы хотим отсюда вывести вот это.
Да.
То есть предложение вложить y в x, что ли?
Now take the image, right? So then we have here surjective map. Here we have a monomorphism. So then what? So this is non-zero if and only if this thing is not zero. And then we just apply this property to the image.
Да, спасибо.
Yeah, so it's kind of maybe in the additive case the definition of a cogenerator or generator makes more sense. Well, because I personally think in terms of this functor that we used today. So, for example, H sub g. So, say this is a generator. Then this will be a functor that relates an abstract setting to the concrete settings of the R modules, right? So, where R is endomorphisms of G. So, being a say generator means that if I take a non-zero object, I'll get a non-zero module. So, quite nice condition.
Здесь, пожалуйста, все очень просто. У нас есть здесь какой-то элемент, в который что-то приходит, что раз это не ноль, то здесь есть элемент в образе нулевой. Ну, сейчас содержит образ. Ну, супер, возьмем h, который берет h от y равно почему-то здесь либо у y бесконечный порядок, тогда вообще что угодно, либо у y конечный порядок, тогда соответствующего порядка, да? То есть, типа...
Сейчас, ну что угодно, как-то не очень понятно.
Ну, сейчас.
Я, ну, в смысле, это вообще любой элемент, что ли?
Любой, не любой, наверное, нет. Если у нас есть как бы это
Ну,
группа, у нас здесь есть просто, ну, y содержит, ну, просто y умножение на z, да?
Ага.
Вот, все остальное мы просто тупо отправляем в ноль, если я правильно понимаю. Сейчас.
Нет. Ну, у вас вы можете определить как бы отображение вот на YZ, правильно?
Ну да, это то, что я сделал.
Да.
Либо это YZ, либо это YZ по NZ. Если YZ по NZ, тогда понятно, тогда Y переходит в, ну, 1 на N плюс Z.
Да. Да.
А если это YZ, то
Ну, 1 плюс Z, наверное, вполне подходит.
ну да. Ну, он же 0 плюс Z, да?
Ну да.
Ну да. И, соответственно, сейчас, нет, он 0 плюс Z.
Сейчас.
1 плюс Z это то же самое, что 0 плюс Z, а 0 плюс Z это 0.
Да, нет, это не годится.
Ну тут надо что-то вообще. Мне кажется, что тут как раз произвольная там, на вторая, например, пойдет, нет? Потому что, типа, каждый четный пойдет в 0, каждый нечетный пойдет на второй.
Ну да, это не нулевое отображение, это нам достаточно, да.
Ну да. А дальше... в общем, короче, я обозначу эту штуку вот так. Ну, то есть она бывает такая и такая. И тогда... Ну, дальше я просто пользуюсь селективностью Купаза, которую мы уже знаем.
Да?
У нас есть вот это вот, у нас есть это отображение Купаза. Оно вкладывается в большой Y, соответственно, здесь есть отображение. И это отображение все еще не нулевое на маленьком Y, все еще маленький Y что-то отсюда приходит, соответственно, композиция не 0.
Ну да.
Не надо, правда, настолько просто.
Еще и место возьмем ядро, чтобы было отображение. Ядро
А какая разница? Погоди, оно ведь было глубокой группы уже. Это просто образ как отображение.
Не, я бы вообще, как бы, то, что здесь написано, я не очень понимаю, зачем нужно. Я бы вот воспользовался этим замечанием и сказал бы, вот у меня есть ненулевой Y, в нем внутри, значит, есть какой-то ненулевой элемент, здесь у меня есть отображение, я продолжаю и все.
Я имею в виду, что
А, так а что это не так, по-моему?
Ну, чтобы строить отображение из образа, это плохо, чтобы потом продолжить.
Погоди, но все еще какая разница, бывает в группе перейдем, там образы кроме это просто одно и то же.
Не-не-не, я, насколько помню, здесь про вот это, да?
Ну да, я имею в виду, что...
Здесь не обелевая группа, есть произвольная аддитивная категория.
Ну, то есть нам же нужно отображение все-таки из X, из образа плохо, он же внутри. А из поинтера хорошо, потому что отображение в поинтере, и оно тоже...
Чего?
Да, и вот отсюда уже нулевое, и тогда позицию надо.
Сейчас отсюда... сейчас. Образ... Сейчас, ну вот это отображение не нулевое, да? Значит, это не нулевое. Но оно же может быть сюррективное, тогда вот эта штука нулевая. Ну, в смысле, эпиморфизм здесь может быть. Тогда...
Ну, если там, где вы показываете эпиморфизм, то это просто изоморфизм.
Тогда, видимо, надо просто смотреть два случая. Если оно не нулевое, тогда, соответственно, есть отображение такое. А, соответственно, если эта штука 0, ну тогда образ совпадает с y и тоже работает. Okay, so next question. R is a commutative domain. Then the Q of R, which is by definition just all the fractions. So this Q of R is injective. Over principle ideal domain, we already know this, but this is true for any domain. Yeah, so in particular, we see that in the category of abelian groups, we have enough injectives. Since we have a cogenerator, any objects can be embedded into some power of the cogenerator.
Почему мы все это делаем? Для того, чтобы, для чего прогресс? Для того, чтобы следующее после нас было как лучше жить. Кстати, трансляция запустилась заново, что?
Ну, хорошо.
Видимо, она пустая, видимо, она не стопла, симпатичная, хорошо. Мне нравится, что в этом кусочке про такой генератор справа сверху аддитивная категория, а дальше мы говорим написано под С. Что-то пошло не так. Типа, я имею в виду следующее.
Ну, я вижу, да. Это тоже довольно простая задача, в том смысле, что ее решение короткое. Но, правда, догадаться до нее немножко сложнее.
Objective это как модуль на это.
Да. Но, как вы видите, вот из этих примеров инъективные модули — это обычно какие-то очень большие модули, они типично не конечно порожденные. Там наличие какого-нибудь конечно порожденного инъективного модуля — это все-таки какое-то такое хорошее ограничение на рассматриваемое кольцо. Но если я ничего не путаю, если кольцо коммутативное и есть конечно порожденный и инъективный, это, скорее всего, означает, что кольцо просто ортинал. Ну, есть два ответа. Один формальный, другой по существу. По существу это нетовая размерность круля 0. Размерность круля 0. Сейчас коммутативная область целостности. Ну, нет. Возьмите полином от бесконечного числа переменных. Ну, Q от R? И как вы разложите прямую сумму?
Нет,
Почему думаете, что R во что-то раскладывается? В каком смысле? На что? М? М, Почему? Ну, не знаю, Z во что он раскладывается? Ну, довольно много есть колец, которые никуда никак не раскладываются.
сейчас, нет, погодите, все-таки элемент D, вот чисто как сумма, это какой-то метод J плюс, ну, как бы, когда мы фиксировали классы бета J, ну это, собственно, может быть.
Ну, давайте я по-другому объясню. Если у вас R разложилось там, в произведение, ну, в прямую сумму двух модулей, да, ну это что означает? Это означает, что они оба проективные, да, ну, они прямые слагаемые свободного, ну, который просто R, свободный ранг 1. Соответственно, это, например, означает, что у вас есть всякие проективные модули, не изоморфные свободному, да. Но есть кольца, на которых там, например, все проективные, это просто свободные.
Кто им мешал быть свободным? Сейчас, погодите, но вот даже на Z у нас любой идеал изоморфен Z как модуль.
Да?
И что, и мне кажется, это не делает никакой проблемы, нет?
Нет, ну вы хотите разложить как прямую сумму, скажем, двух, да? У вас получится, что z изоморфно z плюс z. Ну, если там n штук, то z в степени n, но это невозможно.
Не Z плюс Z, а Z плюс Z плюс Z. И вроде как это не проблема, нет?
По-моему, это большая проблема. По-моему, так не бывает.
Так что это не пойму.
Откуда у вас берется z по nz, как второе слагаемое?
Ну как, я беру число целое, я складываю его, я итерирую его с остатком на n, я беру то, что получилось, и беру остаток. И это дело будет...
Ну, это не будет геоморфизм.
Будет уважать, по крайней мере, сложение. Нет, сложение, но уважать, конечно, не будет.
Ну, в любом случае, R ни на что раскладывать не надо, и, во-первых, невозможно, во-вторых, это не решает задачу. То, что нужно сделать, просто взять и руками продолжить отображение. В смысле, просто формулу написать для продолжения произвольного отображения с идеала на кольцо. Что, у вас есть решение? Ну, расскажите. Хорошо.
Ну, если, значит, есть элемент А принадлежащий G, и это B, ну, если G нулевой, то понятно, все в ноль, а если G не нулевой, то элемент, и, значит, надо сказать, что А делить на КБ, вот, и дальше продолжим по линейности. Надо проверить, что это корректно. Значит, если у нас есть некий другой элемент G, я хочу D, ну, тогда скажем, что надо проверить, что G равно, значит, чему равно, естественно, G А делить на B равно C делить на D. Это то же самое, что G А делить на B равно C делить на D. И надо посмотреть на F G. С одной стороны это К на делить на B, с другой стороны это G умножить на C делить на D.
Я пока думаю, что я до конца не понял, что делается. Вот f это было отображение из идеала q, да? Да.
Вот. И дальше мы просто определяем на единицы, ну, f с волной,
Ага.
да, определяем на единицы и говорим, что это обычный f, и надо проверить, что корректно определено, то есть f с волной g равен f от g, а f с волной от g это вот так.
Ну, то есть, вы, да, понятно, ага.
Ну и надо проверить, что это совпадает.
Да. Ну, в общем, у меня такое же решение, просто обозначения немножко другие. Ну, да. Okay, so let's return to this generator in abelian categories, in abelian groups, and derive from this that we have a cogenerator in any category of modules. So show that hom over integers are few mod C is an injective cogenerator in R modules for any ring R. Ну, нужно проверить, что такой хом это будет инъективное кообразующее в категории левых модулей для любого кольца R. Здесь важно понимать, что R, когда мы хом считаем, мы просто на R смотрим как на абелеву группу. Ну, соответственно, у R еще есть, например, структура правого R-модуля. Тогда, соответственно, этот хом это будет левый R-модуль. Поэтому это имеет смысл. Вот, в частности, из этого сразу будет вытекать, что в категории R-модулей, ну, левых или правых, это не так важно, достаточное количество инъективных объектов, что я сегодня использовал на лекции. Думайте в терминах функторов. Вот у вас есть этот объект, обозначим его Q. Вам нужно, чтобы home над R в Q обладал свойствами, то есть чтобы он был инъективный, функтор должен быть точным. Чтобы он был когенератором, функтор должен быть faithful. Как это по-русски, я не помню. Строгий. Да, вот надо это проверить. А дальше у вас есть всякие вещи, там сопряженность между хомами и тензорами. А, у вас уже есть решение? Ну, давайте. Время, в общем-то, уже выходит. Я думаю, что это должен быть второй аргумент. Даже для инъективности это второй должен быть аргумент. Мне кажется, что вы усложняете. Смотрите, вам нужно вот на такой функтор посмотреть, правда же? Home над R. Ну, здесь какой-то аргумент. Давайте напишем его пока m временно. А здесь должен быть вот этот home z.
Это я просто с стороны написал, да?
Вот я и говорю, что это второй аргумент все-таки. Да, на втором месте. Да, вот в общем, нам про такой функтор, как функтор от m, надо понять определенные свойства, да? До конца семестра. Угу.
И вот он точно, поэтому он переводит, потому что инъективный, значит, вот он точно, поэтому он переводит точно последствия Абеля, но это не важно.
Сейчас, ну здесь, наверное, все-таки не совсем правда написано. Я думаю, что тазное произведение должно стоять здесь с другой стороны.
Да.
Ну, здесь просто как раз вот мы используем, здесь мы как бы вот эту Z-структуру съели, здесь, соответственно, вот она как бы использовалась тазное произведение, поэтому здесь она осталась, поэтому то, что здесь получается, это просто M, на который мы смотрим как левый Z-модуль. Я думаю, этого все не надо, уже все. Вы все решили. Ну, правда, вот у вас есть этот функтор, как функтор m, да? Соответственно, вы применяете как бы к m забывание структуры модуля, оставляете только абелеву группу. Этот функтор, понятное дело, точный. И понятное дело, что он faithful. Соответственно, вы берете композицию с функтором, который вот этот, который точный, потому что это инъективный, и faithful, потому что это мы уже знаем, что это такое кообразующее. Поэтому все. Нет, почему же? Мы берем, смотрим на такой, нам нужно понять свойства вот этого функтора. Да? Вот эта вещь, это будет инъективный кообразующий, тогда и только тогда, когда этот функтор строгий и точный. Правда? По сопряженности переписываем его вот так. Значит, теперь нужно понять, что вот этот функтор строгий и точный. Ну, понятное дело, соответственно, что вот это... Да. То есть мы просто на m смотрим, грубо говоря, как на абелеву группу. То, что вот это произведение делает. Соответственно, получается вот такой функтор, который, ну, вот этот home сюда, он точный и строгий. Потому что мы уже знаем, что это инъективное кообразующее. Но я утверждаю, что если мы из модуля делаем просто абелеву группу, то это тоже точный и строгий функтор. Поэтому это композиция двух точных и строгих, а точный и строгий. Значит, все доказано. Да. А в той задаче про функторы модуля над категорией есть прогресс? Ну, это универсальный ответ теории категорий. Сейчас у вас... Нету еще решения. Ну, направление правильное, да. Мы в следующий раз это обсудим. Я думаю, что на сегодня все.